My name is Anmal Lakodia, and today we'll be proving the Cauchy-Schwartz Inequality. In order to do so, first we will be showing that the dot product of x and y is equal to the magnitude of x times the magnitude of y times cosine of theta. This is derived from the law of cosines. And also another thing to point out first is the dot product is equal to the inner product. Same notation, just whatever we're comfortable with. And also that the magnitude and the norm are the same thing. So, showing that how this is derived from the law of cosines will be the interesting part. So, we will rewrite the law of cosines equation, and it might look slightly different from what we learned in math analysis. However, it is the same, and it will, in fact, show us what we need to simplify this inequality to prove that it's factual. Okay, so the magnitude of a minus b squared is equal to the magnitude of a squared plus b squared minus 2 times the magnitude of a times the magnitude of b times cosine theta. Simplifying this based off of vector subtraction and like the magnitude squared, we would get the magnitude of a squared plus the magnitude of b squared minus 2 times the dot product of a and b is equal to the magnitude of a squared plus the magnitude of b squared minus 2 times the magnitude of a times the magnitude of b times cosine of theta. As you can see from both sides, the magnitude of a squared and magnitude of b squared will get canceled. And so we get left with negative 2 times the dot product of a and b is equal to negative 2 times the magnitude of a times the magnitude of b times cosine of theta. Dividing both sides by negative 2 will leave us with a dotted with b is equal to the magnitude of a times the magnitude of b times cosine of theta, which is the exact thing we were trying to show above. And so this shows us how to derive that statement from the law of cosines. Okay, now in order to substitute it back, first we will split up the inequality. Hopefully this makes sense. So there is an absolute value sign around the around the dot product of x and b, and so undoing the absolute value, we get negative magnitude of x times the magnitude of y on the left side, being less than or equal to our thing in the middle. It's still pretty intuitive, similar to the proof we did in class. And so now we will replace the dot product of x and y with the magnitude of x times the magnitude of y times cosine of theta. And as you can see, we just did that in this step. After this, we will divide both sides by the magnitude of x and the magnitude of y. And that will show us with the fact that negative 1 is less than or equal to cosine of theta, which is less than or equal to 1. We know this is true based off the cosine graph, which oscillates between negative 1 and 1. And therefore, we've proved Cauchy-Schwartz inequality by backtracing up the proof. Hopefully this made sense. I thought it was a pretty simple proof. The only hard part was showing where that one statement from the law of cosine comes from. That being said, we did that very effectively. And so now to show just a couple vectors and what this inequality truly means, we can note that. Okay, so going over examples of why this is important would be beneficial. So going to problem 3, we can note that we did the inner product of b and a, and we got that there was 9. However, if we multiplied the magnitude, we would see that it would be 15. And this follows with what we got from the Cauchy-Schwartz inequality, because it says that the dot product is less than the magnitude multiplied, and that is what happened here. When we're talking about normalized vectors, we can see how beneficial this inequality truly is, because it tells us, and it shows us that the relationship between, what the relationship between our two vectors are. So it can show us if the relationship, if they're heading in the same direction, opposite direction, orthogonal, if we have an acute angle, an obtuse angle. It can show us a lot about where our two vectors are heading. Thank you.